far as doing something called conditional probability. I'll tell you that when you go and take the SATs, I actually have seen some questions that sort of rely on your knowledge of conditional probability. So it's not only a topic for our course and probably in the study of statistics, but definitely something that you'll see on an SAT someday. So for the first part, it says a number is chosen at random for the first 10 natural numbers. So we're talking about anything 1 through 10. Find, and then there's a bunch of probabilities below. I think I just want you to pause quick. Go ahead and try the first 4. If you're feeling daring, try the 5th and 6th example, although I'll tell you right now, those are examples of conditional probability. If you want to just give it a shot and see if you made a good guess at it, go for it. But you should be able to do the first 4. I'm going to show you the answers to those. Okay, so for the first 2, probably that you pick a prime. So I kind of listed the primes that are in the numbers 1 through 10. I hope that you're not including 1 as a prime number. That's one of the most common mistakes students make when listing primes. But we've got 2, 3, 5, 7 in the numbers 1 through 10. So 4 out of 10 would be a reduced probability of 2/5. The probability we pick something that's divisible by 3. So the ones in our list from 1 to 10 would be 3, 6, and 9. 3/10 is the probability there. And then here's my work for the and the or. Remember that and is going to be an intersection of the 2 groups. So if we need to be odd and divisible by 3, I listed all the odds first. And then I boxed in the ones that were also divisible by 3. It's the intersection of those 2 groups. If you think of the like a Venn diagram of those 2 sets. And that 2/10 of a probability would reduce to 1/5. And then if it was odd or divisible by 3, now it can be one or the other. But remember, we have to subtract out any intersecting values. So in my list, there's 5 numbers that are odd. There's 3 numbers that are divisible by 3. And we just determined in this last probability that 2 of them are both odd and divisible by 3. So if I subtract out that intersection, we get that that's 6 out of 10, which reduces to 3/5. So hopefully you remembered that or addition rule from yesterday. But if we have that those events are not mutually exclusive, you then have to subtract out the intersection. Okay. So then moving on from there, how do I do the probability that it's divisible by 3 given that it's an odd number? So what I'll tell you is that when we have something where it's given in our probability, we're actually not looking at the whole original sample space of the first 10 natural numbers. Given that it's odd means our new sample space is only the odd numbers. So the odd numbers are actually going to be the total number of outcomes that go in the denominator. So I right now know this is a probability of something out of 5, because there's 5 odd numbers from our list from 1 to 10. So the probability that it's divisible by 3, given that criteria, well, if I look at the numbers 1 through 10 that are divisible by 3, but given that it's odd, there's only 2 options there, right? So it would have to be 3 and 9. So if you list those numbers out, 1, 3, 5, 7, 9, the only 2 in the list that are divisible by 3 would be those 2. Given that it's odd means that the probability of this happening is 2/5. Now that you know that one, if you want to give the next one a shot, see if you can do that if you didn't get this one correct from trying it on your own. But I'm going to go over this, that if we're now probability of odd given divisible by 3, okay, that's going to be my new denominator. So my new sample space divisible by 3 would be 3, 6, and 9. So this is going to be a probability of something out of 3. Which one of the ones in this list are odd numbers? So we've got 3, we've got 9. So the chances of this happening would be a 2/3 chance that we get an odd, given that it was a number divisible by 3. So that given, that key word there, is what we're going to see when we're dealing with something called conditional probability. So the way we're going to calculate conditional probabilities is we're going to look at the fact that whatever it's given by, that becomes the probability and what's going to go in the denominator. And what's going on in the numerator here is that that is the intersection between the 2 groups, odd and divisible by 3. If you look at this one, this was the intersection of divisible by 3 and odd. Okay. So notice how those 2 things weren't the same probability in the end. Okay. But the intersection actually did turn out to be the same. That denominator is really what changes given based on what the new sample space is. So let me show you first what the notation will look like for conditional probability. If you have the probability of A given B, there's going to be a vertical line that separates A and B. And the way we read that is the probability, just as I said, of A given B. And the way that we're going to calculate that probability is it's the probability of the intersection A and B divided by the probability of what the given part is. Okay, so whatever that second set is, that's the probability that we're dividing by. That's the new denominator. Which means that if I were to reverse this, maybe we're already convinced whether or not these two things are the same, but if I said, what's the probability of B given A, you would do the probability of B and A, which is still the same thing as probability of A and B, but we're going to divide that by the probability of A, because if it's B given A, my new set that is going to be in the denominator there is whatever is going on for event A. Okay, so we're going to do some practice with conditional probabilities. We'll get really used to this wording and this notation as we go through today's notes. The first example says the probability of A is 0.45, probability that B happens is 0.35, and we're given the intersection's probability as 0.10. Find the probability of A given B. Okay, so part A says just get a little bit of practice writing it in the proper notation. The probability of A given B is just what we wrote up above with our vertical line separating A and B, and then use the formula to figure out and calculate what this probability is. So the probability of A given B would be the probability of the intersection A and B divided by the probability of B. So the probability of A and B is given to us as 0.10. Make sure we correctly get the probability of B in the denominator is 0.35. So if I simplify this, which this would quickly become what, 10 out of 35? And if you want to reduce maybe even one step further, 5 goes into the top and bottom to get a final probability of 2/7. Okay. So that's just kind of quick applying based on some given probabilities without any context at all. Here's how we use the formula for conditional probability. Okay, on to the next page. Example 2, we're given a conditional probability. So conditional probability of B given A is 0.85. We know the probability of A and B occurring is 0.6. This says to find the probability of A. So in this particular example, what we're going to do is first I would say, let's set up the formula. The probability of B given A is the probability of B and A happening divided by the probability of A. And probability of A is what we're being asked to find. So hopefully what that means is that I know the other two things. And yeah, if we look up here, we're given both of those. Remember, probability of B and A is definitely the same thing as A and B. So if I sub in what we know, we would get that 0.85 is equal to 0.60 over the probability of A. And you can do a few things from here. If you want to put this over 1, cross multiply. Essentially, however you best want to solve for the probability of A in the end, you should get that the probability of A is going to come out to be 0.60 over 0.85, and 60 over 85 would reduce to the fraction 12/17 if it says something about a reduced form of your answer. Okay, so that's not so bad if I don't know one of the probabilities. I would say more typically you're looking for the conditional probability, but if you don't know one side or one part of this equation, you can sub in what you know and cross multiply there. Okay, go ahead and hit pause for a second. See if you can try example 3. I'm going to quickly fill in my answers here, but hit pause, go ahead and try example 3. Okay, so in example 3, the probability of M given T is the probability of M and T over the probability of T. And if I use the info from above and just plug in what I know, we get that the probability of M given T is 23/24. Is it okay to just reverse those two letters, T given M, and get the same thing? We know that the probability of T and M is the same, but is the probability of M the same thing as the probability of T? I mean, in a lot of cases, the probability of two different events occurring will not be the same. So we still get that the top is 0.23. The probability of M is 0.72. So this probability is 23 out of 72. When you're dealing with conditional probability, that denominator is super important. It's the probability of what that second event occurring is. So do these two things equal each other? I'm pretty confident we would have known that before even heading into this example, but the answer is no. So as a quick conclusion, this is not a commutative process. When you're dealing with conditional probability, you can't just switch the order and say that the probability will come out to be the same in the end. So be careful as far as that goes. Okay. Let's go ahead and move on to a 2A table. So we got two different genders going on. We got male and female, and then we have the number of those different gendered people who are going to college versus not going to college. So to calculate some of these probabilities, I'll do it first few kind of quickly because we should be good at this, I think. The probability that you're female. Okay, so look at the total number of females, which in this case is 22. And then if I want the probability that you're female, you want to divide that by the total number of people in this, let's say, survey of some sort, because this is actually the same example as something we did yesterday. So the probability of female is 22 out of 52. I know that reduces. I'm going to leave it in a non-reduced form for now. Probability that we're going to college, capital C. So the number that are going to college is a total of 29 out of the total number of people in this survey, which was 52 again. And finally, something I hope we're getting pretty good at, female and college, the intersection of those two. Go ahead and kind of trace over female and college, get the number there, which is 13. Okay, so that probability would be 13 out of 52. We should be pretty confident, I would say, to do OR probabilities too, right? Add the two probabilities, subtract the intersection if needed. But now I want to compute what's the probability of C given F. The probability of C given F is the probability that you go to college and you're female divided by the probability that you're female. Now, if you look at the work that we've done already, we've actually calculated these probabilities so far. Probability of female in college is the same thing as college and female. So that's 13 out of 52. And then the probability that you're female just all on its own is 22 out of 52. And maybe you'll see why I didn't want to reduce that right away, because I'm going to use that answer down here. And basically, instead of dividing by this fraction, you can multiply by the reciprocal. You'll see that those 52s cancel. And this is going to reduce this complex fraction. In the end, just becomes 13 out of 22. So the question is, are we going to be pretty good at getting those fractions from the table and dividing those results? I would say for sure we can do that pretty easily. But is there a quicker way just to get to right away 13 over 22? I would say so, and that's what part E says over here. So what's the numerator really? It's the number of people in the intersection college and female. So it's the number of college and female divided by what's my new sample space. Okay, my new sample space, remember the denominator here is just going to be females. So we're just looking at dividing by the number of females, not by the total number of participants in this survey.